Hello everybody. In this video we are going to review chapter 12, the shear strength of soil, and as usual I already posted the worksheet in your blackboard, so you can just take a look and then take a copy of that and try to see this video so that you can understand all the problems what we are going to explain here. I'm also updated the class notes for this chapter so that you can understand that one easily. So take a look at that too. Okay, so we are going to solve some of the problems from chapter 12. So first of all, we are going to cover direct shear test, and you already finished the lab for direct shear test, so you have some idea that how to solve these problems. But I'll show you some of the other problems that would be very helpful to understand. So before that, let me explain a little bit of the direct shear test. So that's the direct shear test box. Sometimes it's a square or cubical shape, and sometimes it's also cylindrical shape. So that depends on, so you have to take a look, like when you solve the problem, that what kind of shear box you are talking about. Okay, so usually we fill that box with soil. So this is basically your soil here. Now what we do, we usually keep either the top or bottom fixed here, box is fixed here, and then try to pull that one with a force S. And when we apply that force, actually that could be either we increase the stress, or what we do, we sometimes actually we do that the constant strain, and then we measure that for that constant strain, what is the stress coming from that strain. Okay, so we have a box from which we can just find out the shear force here, and there is a LVDT here that measures the strain. So what happens, like when this one is trying to move that one, slide that one, then basically either there has to be a crack here so that the top part can slide, and there will be a shear failure within the material. That's basically your shear strength. So before doing that, actually I forgot to tell that one, like you have to add some normal force here. Let's say this one is sigma. Sometimes we call that like, hey, the load is actually P, and if the area of that box in this way is A, so your sigma is basically P by A. Now you can understand, like as strongly we push that one, it would be more difficult to pull that one on this side, right? You already did that one for your lab. So now let's see some of the problems from here. That usually for this test we usually change that sigma 1, sigma 2, and sigma 3. Let's say 10 psi, sigma 1, and then sigma 2, let's say 20 psi, and sigma 3 is 30 psi. And for each of these normal stress, actually we try to find out the stress strain diagram from there. So as you can remember, like if you draw that curve here, like this is your strain and this is your stress, then you will see this looks like this for sigma 1, sigma 2 and sigma 3. This is for sigma 1, this is for sigma 2 and this is for sigma 3. So for each of the cases we have to see that, hey, what is the maximum, stress that the soil can take. That's basically the strength of the soil. So you can see if so that's, let's say, tau 1, this is tau 2, and this is tau 3. Then what we do, actually we draw another curve here. So this one is your sigma, and this one is your tau here. And if you plot the 3 points here, let's say this is sigma 1, sigma, that's the point is 3 points here, and for most of the cases, like for sand and normally consolidated clay, your C is usually 0, means like this curve passes through the origin, okay? That passes through the origin. Now this angle, we call that one phi, right? That's the internal friction angle for the soil. Now that's actually we can do in our direct shear test. And the problem with the direct shear test that like we cannot mimic the side pressure, like confining pressure, and also the other problem is like we cannot mimic the drainage situation, whether the soil is going to drain fast or slow. There is no mechanism here to do that, okay? So that's why we also do like the Tri-Axial test. The problem with the Tri-Axial test is like it's a little bit complicated. It's very accurate though, but a little bit complicated and takes a little bit more time than this direct shear test. Anyway, so I'll talk about that Tri-Axial test later on, but let's do some of the problem from the direct shear test here, okay? So if you take a look in your worksheet, then basically we can just do some problem from there. So let's start from number 2. Actually, number 1 is a Tri-Axial test problem. So we'll solve that one later on. So let's start with direct shear test problem number 2. A direct shear test was conducted on a dry sand specimen. As soon as they say it's sand or normally consolidated soil, this means your C is 0, okay? This is kind of implied there. They will not tell you that the C is 0. But as soon as they say this is sand or normally consolidated clay, this means that they are trying to indirectly give you that information that the C cohesion is 0, okay? The shear stress at failure was measured 20 psi when the applied normal stress is 30 psi. The angle of internal friction of the sand would be, it's very easy, you already know the relationship that your tau is equal to sigma tan phi plus C. But this is dry sand, so your C equal to 0. So they gave you this one is actually 20 psi. This is 30 psi tan phi. So phi equal to tan inverse which is basically 33.7 degrees. Okay, now let's move forward. This is problem number 2. Problem number 3. This one is saying the direct shear test was conducted on a 2, 2 and 1.2 inch height specimen, dry sand specimen. Again, when it's saying dry sand means like your C equal to 0. If the angle of friction of the sand is 24 degree, the estimated shear force required, the estimated shear force, not the shear stress, shear force required to failure when the applied normal stress is 15 psi. So actually your sigma is C equal to 0 and sigma equal to 16. So first of all, you just find out your tau here. Tau is equal to sigma tan phi, and phi is 24 degrees. So this one is 16 tan 24 degrees, which is basically 7.124 psi. Now you have to multiply with the area if you want to find out the force, shear force, right? So shear force here is equal to tau multiplied by the area. Which area? The area, like of contact between these two surfaces. So which is actually 2 into 2, 4 square inch, right? So this one would be 7.124 multiplied by 2 into 2, that's 28.5 pounds. Okay, so the answer is C here. Okay, and I also, like if you take a look, like in your class notes, actually you will see there are a couple of examples from direct shear test there. Take a look there. This one is very, very important too. Anyway, now we are done with the direct shear test. We'll be talking about the tri-axial test. Okay, now this one is we don't have any lab for tri-axial test for undergraduate students. Usually we have a lab for tri-axial test for advanced soil mechanics class, which is a graduate class. Okay, but I'll talk about this tri-axial test a little bit so that you can understand actually what is that tri-axial test and what this one means. Okay. Let's say this is your original grade here, and I'm taking a specimen, soil specimen somewhere from here, which is 20 feet below the soil surface, okay? And the gamma of that soil is 110 pound per cubic feet, okay? Now if you see in this soil element, what is the vertical stress here? That would be gamma sigma, let's say vertical, that would be gamma H, which is 110 into 20 PSF, right? Now, what is the horizontal pressure here? You can remember from your fluid mechanics, actually for any kind of fluid, the horizontal force is equal to the vertical force, because for liquid, the pressure works similar to every direction. For soil, it's not true, okay? But what's the horizontal pressure here? That's basically, we don't cover that one in this course, which will be covered in the next course actually. But usually if the phi of the soil is 30 degrees, then basically you will see that your horizontal pressure is half of your vertical stress, okay? Half of your vertical stress. So if I take that soil element here, so you can see this is 2.2 KSF, and let's say this is 1.1 KSF, so that the soil is this is the loading situation of the soil element. Now you can see here that at the beginning we don't apply any shear force at the top or side wall of the soil. But here you can see there is no shear force here or here, here or here, because these are principal plane, and you know that principal plane, your shear should be 0, right? So these are principal planes. But when we apply that vertical force, that will create shear force in different angles, right? If you say like, hey, I want to see that, hey, what is the shear force here, then you will see that your shear force is not 0 in that particular plane. So it will create shear force automatically at different angles, and if this shear force is higher than the shear strength of the soil, then basically the soil will slide at that particular angle, okay? Now, the problem with the direct shear test, you can see we cannot apply this like confining stress there, right? That is a solid wall there, but you cannot change the stress there, okay? That's the first problem. The second problem is, you can see that like the soil depends on the type of soil. If it is clay soil, then it might take like sometimes 20 years, 30 years for consolidation, right? So the drainage is very, very important in that situation. In direct shear test, actually, we cannot mimic that drainage thing down there. So that's why, like this test is much more important than the other one. But the thing is, like for normal 2-storied building, 3-storied building, like the direct shear test or SPT value would be good enough to find out the shear strength of the soil. On the other hand, for skyscrapers or very sensitive structures, we must have to go for Tri-Axial test. Tri-Axial test is definitely much more expensive than the direct shear test, because it takes much longer period of time, sometimes take 2 weeks to finish just one sample, okay? So that's why we try to not to, like even though very accurate, but sometimes we try to avoid that test to save some time. Anyway, let's move forward now. So I'm changing that one right now, just for example, I showed that one to you. But the general case, this one is your sigma 1, and this is your sigma 3. So if I draw the Mohr circle with this one, then basically you will see so the center would be here. You know the center is actually sigma 1 plus sigma 3 divided by 2, 0. Okay? And now let's say that this is a sand, so that the cohesion is 0. Okay? Now if you draw the Mohr circle here, this is your sigma 1 and this is your sigma 3. That's the Mohr circle. Now you can see also that from the Mohr-Coulomb's theory that the soil will fail at a particular combination of your normal stress and shear stress. And the failure envelope, this one looks like so the line, basically this one is tau is equal to sigma tan phi plus c, but c here is 0, so I'm just putting that one here. Okay? Now if you see, your book has this figure from there, and from that figure they have 2-3 different relationship or formula that you might have to use in your to solve these problems here. Okay, so that's the failure point here. So we usually call that one sigma f tau f here. Now the important thing is like, what is that angle that's making with the positive x-axis? If you know that theta here, then basically you can find out what would be the shear stress and normal stress on that failure plane, right? Because you already did that one in chapter 10, like stress transformation cases, right? Now let's say this one is twice theta, okay? Then this one is 90 degree. Let's say this is alpha and this is your phi. So you can see this one is 180 degrees, so I can say 2 theta plus alpha equal to 180 degree is equal to alpha plus 90 plus phi. So you can see in this equation alpha alpha cancels, so your theta would be 45 plus phi by 2. So this angle here, actually theta, is equal to 45 plus phi by 2. So if I give you this information here, like this is my sigma 1, this is my sigma 3, my tau xy equal to 0 because there is no tau xy here, find out the normal stress and shear stress at a plane 45 plus phi by 2. So you can just use those equations given in chapter 10 and plug the value there, and you can find out the sigma n and sigma and tau n easily, right? So that's one of the things there. From this information here, we can also get another relationship which is called the sigma 1 is equal to sigma 3 tan square 45 plus phi by 2 plus 2c tan 45 plus phi by 2. If your C equal to 0, then basically your sigma 1 would be sigma 3 tan square 45 plus p by 2. This one is when your C equal to 0. When C equal to 0, just for one more time, if the soil is sand or normally consolidated clay. Normally consolidated clay is usually so loose that the particles don't touch them that strongly, and that's why even though it's clay, doesn't show any cohesion. Okay? Now, from here you can also see one more equation that you might need. That's actually, if you see here, sine phi. In this triangle, sine phi, this means like OB divided by OA. So OB is basically the radius of that circle, right? So the radius is basically sigma 1 minus sigma 3 divided by 2. And what is OA? OA is nothing but the distance from here to here, which is actually sigma 1 plus sigma 3 divided by 2. So you can see your phi here is actually sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3. So we might have to use this equation to find out our phi many times, okay? So from that figure we already got these equations. One is sigma 1 is equal to sigma 3 tan square 45 plus phi by 2, and theta, the failure angle, is actually 45 plus phi by 2, and you can find out also phi from here, which is equal to sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3. Okay? Now let's talk about like, hey, why we are doing so many different, like Tri-Axial test, right? CD test, CU test, and UU test. Why? What does it mean actually, right? Now let me show that one to you a little bit. Let's say this is sand and this is a clay layer. Okay, and now I'm just trying to find out, hey, what would be the tau here in the middle of that layer. But you see that like your shear strength for CP soil means like either sandy or the mixture of sand and clay. That's a function, right? It's not a number, it's a function. And this function is, your tau is equal to sigma tan phi plus C. Okay? Now, let's say for this particular clay layer, not clay layer, let's say, yeah, it's kind of like a mixture of sand and clay. Yeah, we can just say like low plasticity clay. Now if you want to find out the tau, now you have to say like, hey, what is your sigma here, right? But before sigma, this is your sigma basically here, like I'm gonna make a structure here. That's actually from there. This one, let's say, is del sigma prime, which is, let's say, 1 KSF. Okay, and let's say this one is 10 feet, this is 16 feet. Here, the soil gamma is let's say 120 PCF, phi equal to 34 degree, and here you have your water level here, and let's say the gamma sat here equal to 115. And C is equal to 200 PSF. PSF. Okay. Now, what would be the strength of that soil at point C? Now, it's not that difficult here. You can just plug all that values here. Only important thing is here. This one is basically the effective stress. Okay? All other stresses remains, all other things are fixed here, because you can see this is sigma prime, 10, 20 degrees plus actually 0.2. Now, what is your effective stress at this point? You can see that the overburden pressure here is 120 into 10 plus 115 minus 62.4 into 8. 8 is the midpoint, that's why I'm just keeping that one. That's your overburden pressure. And then you can see that this much force is coming from the new force, from the new structure. Now what will happen, like, as soon as you apply that load, who will take all this load in this layer? Because this is clay soil, this one has to go for primary consolidation settlement. So at the beginning, you will see that all the load is taken by the water, right? So at time t equal to 0, you see your sigma prime would be actually this overburden pressure, and at the beginning del sigma, this one is actually 0, right? Now you can see when the consolidation occurs, then basically this one would be sigma prime plus. So you see that basically your effective stress is changing with time, right? And this time is a function of what kind of soil we are talking about. Definitely this one is applicable only for clay soil, because for sandy soil the water will drain very quickly and you will see that this one will be this one. You can calculate this one based on this equation here. But for, let's say, this soil takes like 15 years for fully consolidation, right? But I'm making that structure in 2 years. So by the end of the construction, 2 years, you will see only like 5 to 10% consolidation occurred. Means like only 5 to 10% of the total load applied here is going to the effective stress. So if your effective stress is low, means like your shear strength is low, right? If your effective stress is high, means like your shear stress is high. So basically with time you can see your shear strength is changing. So that's why drainage is very, very important, that how fast this one is draining. So based on that, actually we tried like the Tri-Axial test, 3 different scenarios. First of all, the soil is draining fast enough that if, let's say, the structure takes 3 years construction, then by that time the overall consolidation settlement will be occurred. That's case 1. We call that one CD test, consolidated, drained. Means like all the time the pore water pressure will be 0 because the construction is slow enough that the water can drain out from there easily. And then for high plasticity clay or CH soil, let's say this one will take 15 years for draining and your construction time is 1 year. So the first year you will see only a very small amount of the total stress is going towards the soil, and most of the stress will be taken by the water. Okay, so that's the extreme case. So we call that one undrained shear strength, which is the lowest strength of the same soil. Okay, and the direct shear test is the highest, and then in between we have CU test, consolidated undrained test. So we usually apply confining pressure, then we allow the water to get out from there, and then when we apply the vertical force or shear force, then basically at that time we try to close the valve so that the water cannot drain at that particular time. Okay, so based on that you have 3 different set of like mode circle, and because for completely undrained situation you can understand that like every pressure you put from there actually will be taken by the water because water is not draining from there. So you cannot change the effective stress on the soil. So your strength remains same. So yeah, let's now go back there. We'll talk about each of the problem and then try to see how this one plays. So let's start from number 1 here. So problem number 1 is saying for a normally consolidated clay, so as soon as it's saying normally consolidated clay or sand, it means like your C equal to 0. Okay, so C equal to 0. And then they're saying that phi is equal to 26 degrees. Phi prime. Okay. Phi prime here. In a CD test, the specimen failed at a deviator stress of 23 psi. Now, before let me do that one, let me explain a little bit of like what is that deviator stress and what is like all that stresses here. So for your Tri-Axial test, you can see, let's say this is your soil specimen, cylindrical. Usually all the time we take cylindrical soil specimen. that's a porous stone here. And then we keep the whole thing inside a tube, membrane, okay, rubber membrane. And then lock that one here and here with O-rings. So they are inside, like the membrane here. Now the whole thing we put inside a water chamber, okay? And now from here, actually you have two lines here. One is just to drain the soil from here, and one more line here which measures the pore water pressure here, okay? Now, first of all, what we do, we just fill that chamber with water, okay? Now this one is, let's say, closed. The valve is closed, so no drain. Now let's say I'm changing my pressure here from a control board. I have a knob there. I can change, like, let's say I want to apply 10 psi load, okay? So let's say the water pressure, sigma 3 actually, let's say 10 psi. So you can see the whole thing here will be under 10 psi pressure, okay? So if I show that one here, every way I have 10 psi pressure. So what will happen when we apply that? Try to compress the soil from every side. The soil will try to consolidate it, right? The some of the water inside the clay soil will try to get out from there. So here you can measure, like if I apply 10 psi at the beginning, the pore water pressure would be 10 psi, right? At time t equal to 0. Then you open that valve. What will happen? The water will try to get out from there, and this one will go down, 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 down. At a certain time, this pressure, excess pore water pressure will be 0. This means the soil has already consolidated, right? As soon as the consolidation occurs, then basically you apply load here, the vertical load here, very slowly, okay? And let's say this one we call the deviator stress. Sorry, deviator stress. And when this one fails, we measure that one. We call that one deviator stress at failure. Okay? Now, so there is two situations. First of all, when you are applying that confining stress, is that time this one is open. If this is open, and when you are applying that shear, that time this one is also open, means like the drainage is occurring all the time, then we call that one CD test, okay? Consolidated drain test. You are allowing consolidation, and then you are also allowing drainage, like when you apply that shear, okay? Now if you see here that when you are applying this one here, then basically you are applying additional force of this is your deviator stress, okay? So if I Now draw that one here again. Then this one is your sigma 3 all around pressure, and this one is your sigma 1, which is basically sigma 3 plus your deviator stress. Okay, so deviator stress del sigma df, that's basically sigma 1 minus sigma 3. Okay, that's your deviator stress. Now let's do this, go back to this problem here. So this one is saying that the specimen failed at a deviator stress (23 psi). They are asking what is the confining pressure, sigma 3. Okay, sometimes we also call that one all around pressure, confining stress, confining pressure, or all around pressure. Okay, all around stress. Now you know, so here you can see your sigma 1 is basically sigma 3 plus deviator stress Now you can see here, we know sigma 1 is equal to sigma 3 tan square 45 plus V by 2 plus 2C, but this one is 0, so I'm not writing that one here. So you can just say like sigma 3 plus 23 is equal to sigma 3 tan square 45 plus 26 by 2. So if you solve that one, you get your sigma 3 is equal to 14.7 psi. Okay, now let's move forward. This is actually problem number 1. Problem number 4 to 7, actually the same thing here. So I'll just say 4 to 7. This one is saying that a CD tri-axial test was conducted on a normally consolidated clay specimen. The confining pressure sigma 3 is 300 kPa and the deviator stress at failure is actually 350 kPa. So what's the angle of friction of the soil? Okay, so you can see here, first of all, number 4. That's a CD test conducted on a normally consolidated clay specimen. As soon as this one is saying that normally consolidated clay, this means your C equal to 0, right? So at that time, C equal to 0, sigma 3 equal to 300 kPa, sigma 1 is equal to sigma 3 plus deviator stress at failure Now we know that phi is equal to sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3, which is sine inverse 650 minus 300 One thing try to remember for CD test, your valve is open all the time, means like actually your pore water pressure is always zero. And you have to apply the load, either confining stress or the vertical force, so slowly in your CD test that all the time the pore water pressure will be zero. Okay? So for CD test, your phi is actually your phi prime and your because your pore water pressure is zero, right? So effective stress equal to total stress minus pore water pressure. So when pore water pressure is zero, then basically your effective stress is always equal to your total stress. So the strength parameter for phi and C would be equal for effective stress and both like total stress cases. Now let's move forward. There say the angle that the failure plane makes. Okay, so if I draw that one here, so you got your sigma 1 and sigma 3. This one was 300 kPa and this one is 650 kPa. Now this one is actually asking that what angle this specimen is going to fail, right? So that's your angle theta. Okay, but we know number 5, we know theta is equal to 45 plus phi by 2. So 45, in the previous problem number 4, we already got the value of phi, which is 21.6. So this one is 55.8 degrees. So this is 55.8 degrees. Okay. Now they're also asking like, hey, the normal stress sigma on the failure plane in that particular plane. Okay. So you just go back to chapter 10 now. So you can see here sigma 1 is basically 650, sigma 3 equal to 300, your angle theta measured, positive x-axis counterclockwise is positive, so this one is 55.8 degree. Okay, what else? Tau xy. That's actually 0 because I don't see any tau here, right? So we know from chapter 9 that sigma n at any particular angle is equal to sigma 1 plus sigma 3 divided by 2 plus sigma 1 minus sigma 3 divided by 2 cosine twice theta plus tau xy sine twice theta, right? But tau xy equal to 0, so I don't need that part here. So you just plug those values here and find out what would be your sigma n. So 650 plus 300 divided by 2 plus 650 minus 300 divided by 2 cosine 2 into 55.8 degrees. So you got 410 kPa. Okay? So we are going to use the information what we learned from chapter 10 here. Now problem number 7 is actually asking the shear stress tau F on the failure plane. So this one remains same here. Number 7. Okay. So for number 7 we know that tau n is equal to sigma 1 plus minus sigma 3, sorry. Minus sigma 3 divided by 2 sine twice theta. And then you have like your tau xy, which is actually 0, so I'm not going to write that one here. So you just plug these values here. You can see 650 minus 300 divided by 2 sine 2 into 55.8. That's basically your 163 kPa. Okay, so that's basically the same thing, like that I showed at the beginning. Okay. Anyway, now let's move forward. We are going to show like 2 problems from CU test. Okay, so let me explain CU test a little bit, so that you can understand that one easily. Okay. So as I showed you earlier, that let's say this is my soil specimen here. There is a line here for drainage. If you open that valve, then it will drain. If you close that valve, it can drain. Okay, so now you can see there is also a transducer that can measure the pore water pressure. Pore water pressure. Now whole thing is inside a water chamber, right? So here you can just apply water pressure here. Now let's say I apply the a confining stress first here. Fill that one with water, and all around pressure, let's say here is 10 psi, okay? And once you apply that 10 psi, usually we don't apply 10 psi at a time. We usually apply 1 psi first, and then after 30 minutes or an hour, we'll change that one to 2 psi, so that I'm applying pressure and the soil is trying to shrink because you are trying to push that one all side, right? So some of the water has to drain out from there, and you will see as soon as I apply 10 psi pressure, this one is theoretically should be 10 psi here. But since the valve is open, so basically during that consolidation time, we are applying that pressure so slowly that all the time that pore water pressure will be 0. This means like during that time your effective stress is equal to your total stress, okay? Now, what about when I apply that shear? For CD test, this valve will be open when I apply that shear force here, okay? From outside, very slowly. So this one is your deviator stress, right? Sigma dF, that's actually P by A. P is the force, A is the area of that cylinder, okay? Now when you start applying this one, that time actually you close that valve, okay? So when this one is consolidating, that time this valve is open, so drainage allowed. When you are applying that shear force here, after consolidation, then basically this valve is closed. So what will happen when you are applying that load, you will see that this one will create some pore water pressure here. And when this one fails here, then basically you will record a pore water pressure at failure. Okay? Now let's get back to the Mohr circle for this one. For a normally consolidated or sandy soil, this one looks like this. So this is your, let's say, sigma 1. Now this is sigma 1 and this is sigma 3 in terms of total stress. Now you also measured the pore water pressure at failure. So if you subtract that pore water pressure from sigma 3, then basically you get sigma 3 prime. So this is your pore water pressure that you measured at failure. Okay? Similarly, if you subtract that one from here, then basically you will get sigma 1 prime. So the distance between this one is basically here. No, actually I made a mistake here. That would be the other side, other way around, right? Because you are subtracting something from here. So that's basically your sigma 3 prime. Similarly, this one is here. So if you subtract your pore water pressure at failure, then basically you get the effective stress. Now from there you can just draw another circle here. So you can see this one in terms of effective stress, and this one is in terms of total stress. Okay? So if you think separately, like this one and this one, then basically all the formula that you developed from this figure works for both of them. Okay? Now let's see how we can use this information to solve our problems. So problem number 8 and 9, this one is saying the consolidated undrained Tri-Axial test on a normally consolidated clay. When said normally consolidated clay, then C is basically 0. Actually in this book, like we see that for your course, most of the cases C equal to 0, because otherwise this one would be too complicated. Okay, so that's why I see most of the problems given in this book is actually C equal to 0. If your C equal to not 0 means like if you have over consolidated clay and you do that test, then basically you have to do at least 2 tests, okay, to get like your C values. Okay, so that's kind of complicated. That's why most probably they didn't include this type of problem. So I'm not going to include that one in your exam too. Anyway, so here this one is saying that a consolidated undrained Tri-Axial test on a normally consolidated clay was conducted at a confining pressure sigma 3 is 12 psi. So this is CU test, and now you have to be very careful with the total stress and effective stress because they are different. In CD test you didn't care because the total stress is always equal to the effective stress because your pore water pressure was always 0. Here this is not the case because you kept the valve closed during shearing and that created pore water pressure. Okay, so here sigma 3 is 12 psi, deviator stress at failure, and is equal to actually 9.14 psi, and your pore water pressure at failure, which is 6.83. Now number 8 is asking the drained friction angle. Drained friction angle means what is your phi prime. Okay, so you can see here that your sigma 3 prime would be sigma 3 minus your pore water pressure, which is 12 minus 6.81, .17 psi. What is your sigma 1 here? Sigma 1 is basically sigma 3 plus deviator stress at failure. So that would be 12 plus 9.14. That's actually 21.14 psi. So what would be your sigma 1 prime? That would be sigma 1 minus your, so that would be 21.14 minus 6.81. That's actually 14.31 psi. Now we know that phi prime would be equal to sine inverse sigma 1 prime minus sigma 3 prime divided by sigma 1 prime plus sigma 3 prime. So when you are writing that equation, you have to be very careful. You are writing in terms of effective stress everything, right? So you are following that Moore circle for effective stress. For total stress, this formula looks like this. Sigma is equal to sine inverse okay? But anyway, we are not going to use this one here. They ask you to find out that phi prime here. So you can see this one is sine inverse 14.31 minus 5.17 and then 14.31 plus 5.17, which is basically 28 degrees. Okay. Actually, problem number 9 is saying that what would be the friction angle phi. It's in terms of total stress. Okay. So if you see this one here, only difference would be so that's problem number 9. So for problem number 9, you can see this one is phi is sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3. So this is sine inverse sigma 1 is 21.14 minus 12 that's basically 16 degree. Okay, so the top one is 28 degrees, this one is 16 degrees. So if I draw that one here, what does it mean? So you can see here, for sigma 1 was 12 here, sigma 3, sigma 1 is 21.14. So this angle, this is in terms of total stress, so this one is 16 degrees, okay? In terms of effective stress, I subtract the pore water pressure here and pore water pressure here, and this one is 5.17, and this distance is basically your pore water pressure, which is 6.81. Similarly, if I take 6.81 from here, so this is my sigma 1 prime, which is actually 14.31, and if you draw the Mohr circle for effective stress, and this is your phi prime, which is actually 28 degrees. Okay, phi prime, this is your sigma 3 prime, this is your sigma 1 prime. Okay, so this one is the red one. On the other hand, this one is in terms of your total stress here. Okay, anyway, let's move forward. Now we have to do like your UU test. So what happens in the UU test? That your drainage is always closed, okay? When you apply this confining stress, then basically your drain is closed. What does it mean? When the drain is closed, means like all the applicable confining stress will be taken by the water, right? Because the drain is closed. So basically your effective stress means the stress in the soil is not changing even though I am trying to push that one like this. Similarly, when I'm applying that vertical force, that time the drainage is completely closed, means like all the load will be taken by the water, so actually the effective stress remains same, it doesn't change. Okay, so we see since effective stress doesn't change, remains same, this one is somewhere here, but you can change your total stress. You can apply more confining pressure, you can apply more vertical pressure, so your total stress is changing. But when you're changing your total stress, actually all the load will be taken by the water, so actually effective stress is not changing. So that's why for UU test, we always put that one in terms of total stress, okay? So total stress circle looks like this. If you change your sigma 1 and sigma 3, this one goes like that. Okay, so basically if you draw the line here, this one becomes here, the time we call that phi equal to 0. Okay, so this one is parallel to the x-axis, so phi equal to 0, and that time you can see your strength C is basically nothing but half of the radius, right? This is your radius. So sigma 1 minus sigma 3 divided by 2. That's basically your UU test. So when you are trying to prepare yourself, you just trying to think like I have 3 tests there, CD test, CU test and UU test. And for each of the tests, how the Mohr circle look like, okay? Try to remember that one inside you. That would help you a lot to solve these kinds of problem, okay? Now, let's see the other problem here that this one is saying, the last problem here is basically saying, number 10, an unconfined compression test was conducted on a clay specimen 2-inch dia and 4-inch height, okay? So unconfined test, basically a UU test. Why this one is called unconfined? Because sigma 3 is 0 here. It's not confined, okay? Usually for clay specimen, we just put that one on top and then try to apply load here and see that when this one fails, okay? So sigma 3 is basically 0, that's why we call that one unconfined. It's not confined, but basically unconfined compression test is a UU test, okay? Why it is UU test? Because we applied that load fast enough so that the water cannot get out from there. But this is a much faster test, okay? So that's why this is a UU test. Now they are saying that an unconfined compression test was conducted on a clay specimen 2-inch dia and 4-inch height. If the specimen fell at a compressive force of 50.25 pound, the shear strength of the soil is so you are applying here 50.25 pound. It fails. So what was the stress at that time? Sigma 1 is basically here is deviator stress plus sigma 3, but sigma 3 is 0. So deviator stress was 50.25 divided by the area, and the area is pi r square, r equal to 1. So that's basically 16 psi. Okay, so here this one is causing 16 psi load. That's your sigma 1. Okay, sigma 3 equal to 0. So if I draw that more circle here, you can remember that sigma 3 is 0 here and sigma 1 is 16 here. Since this is a UU test, so your phi has to be 0, okay? And that's your C. But sometimes you also call that one CU because it's coming from the confining stress. It's coming from your unconfined compression test. So you can see your C is nothing but the half of the radius, right? Half of the diameter, because it's the radius here. So what's the diameter of that thing? That's actually 16 divided by 2. So this is the diagram for unconfined compression test, okay, which is a very common test because it takes very small time to do that one, okay. So that's about it for this chapter, and also try to take a look like here. I'm gonna also post the video for the second exam review, so take a look over there, and if you have any question, please try to contact with me. Thank you so much. Appreciate that.